So welcome everybody to the fourth session. Is this fourth? Fifth session already. Oh my God, we have been doing this for a long time already. So welcome to the fifth traditional AI Helsinki meeting. We started this so that everybody would start learn what everybody else is doing. At some point, everybody knows what everybody else is doing, and we need to figure out what else to do. And one of the things that we figured that everybody needs is to learn new things. And in the future, I think AI Helsinki might turn a little bit into kind of private university. So we are going to start AI learning courses, machine learning, deep learning, AI. We are going to organize study groups. I'm not going to say more about that now, but in the next meeting, we should be able to talk more about that. And we already have 2 speakers confirmed for the next session, which is going to be on 15th of June. One of them is the inventor of backpropagation, Seppo Linnainmaa. So remember to be there also next time. I'm also going to speak next time, and then we're looking for at least one other speaker. This time we have also 3 speakers. The first speaker is Dorota Glowacka from Helsinki University. She has been working on reinforcement learning and other things, and in particular in connection with trying to get systems helping humans. Isn't that right?
Yes.
Roughly? So now she's going to talk about how to make that happen for real.
Okay, thank you. Okay, so the title is Optimizing Machine Learning Systems with Human Input. It maybe sounds a bit vague, but basically what I'm trying to talk about today is, well, there are lots of researchers in machine learning in this room and so on. A lot of algorithms are being created, but the question is, well, once you have these algorithms, then you actually want to build real-life systems that use them. And a lot of my experience is that once you actually build a system, put a nice algorithm that in theory should work, and the simulations were perfect, all of a sudden the system does not behave as you expect it to be, and people are not happy. So maybe I should just start with my background and how I came to do this type of research. So I actually did PhD in machine learning from at University College London. It was in John Taylor's group, so quite a strong machine learning group. And during my PhD, I did a lot of work on algorithms that, that tried to learn from interaction. So there was a lot of reinforcement learning research involved in it. I was involved in an EU project where it was related to, specifically to content-based image retrieval. So there, we tried to investigate how to learn from feedback and so on, from relevance feedback, which type of features and which type of images are relevant. Initially, a lot of my research was based on simulations. We were trying to figure out, we built a new algorithm that we assumed that, relevance feedback should be like this. Then we had a lot of simulations. We just say, this algorithm is perfect. It works. And, I thought, yeah, the PhD is going great. Everything is perfect. Until one day, I was sitting in a pub with my colleagues, also doing PhD, and someone, I think it was someone from the networking group, said, well, how do you actually know that the simulations make any sense, right? What if you actually put this algorithm somewhere? Will they work? Will it make any sense? What about, are your assumptions correct? So I thought, well, I'm just going to try and see what's going to happen. So what I did, we built this extremely simplistic system, as you can see. But I was so proud of myself. I thought, now I'm just, it's not just algorithms, actually doing some real stuff. So the assumption, I'm not going to go into it, the assumption of the algorithm was, well, you click on an image as a user, and then the algorithm will try to figure out what you're looking for. So we thought, and the assumption was that, the user has some image in mind. So we thought, yeah, we just show someone an image and we just tell them, now look for this image. So there was the experimental design. Then, we just show people a number of images and we said, just click on these images until you find what you're looking for. There was no design involved. There were no actually usability studies. We just, we just built it and we said, yeah, we're just gonna use it, and because we're just so great. Initially, we don't even, like here, you just click on next to go to the next iteration. Initially, we didn't even have that. So what I had was like, yeah, so people just keep on clicking on these images and they get to the end. And then someone was doing the experiment and said, well, so how do I end it now? How, where does it end? I thought, oh no, so now, yeah, we just have to click on this one and the experiment will end. So it was all these, coming from a totally different background, trying to design a working system was like, yeah, I just don't know what I'm doing. So that was how I decided to actually go into research where, fine, you work on machine learning, you design your algorithms, you actually try to also build real-life systems with this algorithm and optimize them to make sure that they work that they were designed for. So what is my research now? So I've been at the University of Helsinki for 4 years now, and my initial research is was part of the heatwaves focus area research, where what we work on is I would call exploratory research. So now I'm kind of moving into information retrieval slightly and HCI-oriented research and machine learning. So it's all this big area called exploratory research. So just imagine, search can be divided into two broad areas. So you have lookup, and that's what everyone knows and everyone does. It's the Google-style search. You type in a very specific query. You want to have a very specific paper or answer to a very specific question. There pops an answer, 10 ranked documents and so on. Everyone's happy. Now, exploratory research, and this is becoming very, very popular nowadays because of the amount of data that we have in general. In exploratory research, what happens is like, well, you don't know yourself what it is that you're trying to find. You're a student, you take your first course in machine learning. How do you actually explore this area? What queries do you even type in a system? What do you expect to find as you go along? So it's a very challenging area of research in general that combines these three fields, which is machine learning, HCI, and information retrieval. How do you then support this type of research where you as a user, you say, I don't know what I'm trying to find, just help me. So in this, reinforcement learning techniques are actually very popular in general because, well, what they actually help us to do, they balance this exploration, exploitation, and as the user gives more and more feedback over iteration, the system will build a user model over a search session. So, initially you may give the system a very vague query. So the system will give you maybe sort of slightly broader papers and so on. But as you sort of learn more about the search area and you give more and more precise feedback, the system will narrow down and gradually build your user model and help you find exactly what you want. Now, we built a number of this type of systems over the last couple of years, but the problem was, you use these perfect algorithms. We use a lot of bandit algorithms, to be more specific. But now all these algorithms have some parameters, and now it's all great, and the simulations work, and there are upper bounds and so on. But how do you actually parameterize these algorithms so they work for people? Because people who use these systems often say, well, they feel the system actually are not responding to what they want. And they just say, well, the system just behave in such a random way. So what was our hypothesis? So we thought, well, the mismatch between what user want and need from these systems And how the system performs is not because of the algorithms that are being used in the systems per se, but it is how these algorithms are being optimized and put into the system. So if you don't tune these bandit type algorithms, so let's say the expiration rate is too high, then the result seems to be totally random from the user perspective. If the expiration rate is too low, then people say, the results are just so narrow. I got stuck in this extremely tiny, narrow information space, and I cannot get out of it, and so I cannot find what I actually need. So we thought, so if I hypothesize the exploitation trade-off can be modeled as a relationship between, the exploration rate and how many documents, for example, we click on with a specific exploration rate. And this is based on literature from information science, information retrieval. The more people click on, the more engaged they are. So we thought, the more they click on, then this particular exploration rate should be best for this particular system. So in order to test this, this is one of the systems we've been working on recently. Also, our assumption is we want to actually use literature and data that would be used by someone. We don't want to have just simple toy examples. We just want to work on real-life data that people will be using. So this is our recent system, we downloaded the entire arXiv, and we thought it's going to help students in the department as well, so it's not going to be just some tiny research system. We call it Pulp. So we thought the interface has to be pretty simple, so that people are not distracted by the interface itself. It looks kind of Google-like. You can type in a query, then you give a set of documents. You can click on the documents and give feedback just by clicking on the document, so we know you like this document and so on. So this is based on the bandit algorithm. So each document is an arm of a bandit and so on. So once you click on number of documents, you click next, and you go to the next search session. And this is how the system will try to figure out what you want. So the underlying algorithm, it's called Linwell. It was proposed by Peter Au. It's one of the first contextual bandits algorithm proposed by Peter Au in 2002. So just to briefly go over it. So you can see basically it's a regression model. So xi, the small xi, is our specific document. Then the big x's are a set of documents that the user has seen so far. And then for each document, we calculate this AI, which is the output of the regression model. Then after we calculate the regression model, we combine it with the user feedback, or the documents they've seen so far, which is the Y. And after that, we add some, what we can say, noise to the data. So we just, with the second, I can actually show it very well. But the second component in the second regression, which is C over 2, this allows us to then control how exploitative or exploratory the documents show to the user will be. So the higher the C value, the more you explore, so the more diverse the documents will be. The lower it is, the more exploitative the documents will be. So in our case, the main problem was to set the C value to the correct, to give the correct number to the C variable. And, and this is also one of the reasons why we selected a pretty simple algorithm, because we just don't want to have too many variables. We just want to see how to set it, how to set just one parameter, and how trivial, well, we thought it was going to be trivial, it's going to be. So how do we go about actually setting this one tiny parameter for the entire system to make it work for a specific set of users, or a group of users? It didn't turn out to be as trivial as we had thought. So we thought, okay, so first we just run some simulation studies with different values of C. So the C value can go from 0 up to infinity, effectively. When it goes to 0, then the system does not really explore. It just gives you the set of documents that are very, very closely related to your query or the documents that you've clicked on so far. So what we did, we just thought, well, we just run the number of simulations and we see by increasing the value of C, how many exploratory documents we're going to have compared to this perfect ranking. So we thought, we're going to go from 0 up to 50%. Then after we got these values for C, we ran a number of user studies where we had MSc and PhD researchers from the department. We tried to make sure that the level of knowledge of machine learning would be more or less the same. So there were MSc students writing up the MSc projects and first-year PhD students who just finished their MSc. We gave them 5 queries. Everyone was doing the same 5 queries. That I don't remember exactly. I think it was clustering, neural networks, and so on. Underlyingly, each query had a different exploration rate, and we told them, just go for about 20 minutes and tell us what you found out about this specific topic. They all had more or less the same level of knowledge for all the topics we've studied. Now, in the analysis, as we said, we wanted to see the relationship between the exploration rate and how engaged in terms of clicking on documents the users would be. So it was modeling combined with qualitative analysis with user performance. Right, so this is the simple regression model we got. Obviously, we cannot get loads of people, so the regression model is always a bit wobbly. But so at exploration rate 1, which corresponds to about a quarter of the displayed documents being exploratory, we got the highest engagement from the users. So when the C value in our algorithm is set to 1, we get the highest engagement. So now it's like, we have this model, so does it actually correspond to what people also liked? So we had user feedback and interviews after each experiment. So, when the exploration rate was 0, so there's basically the system was only exploiting what we got. This is a typical response at this exploration rate. They said, well, results are not quite satisfactory and about very specific definitions. I didn't get to understand what topics there are in this area. Now, exploration rate 2, this is the C value was 2. And this is where about 50% of the documents were exploratory. What we got was results are too scattered and there are too many topics that are non-related. Now, at the next level, the exploration rate was 1. So this is when they say, I went over several iterations, results started getting way better, and overall, I'm very satisfied with the results. So this is how we go about setting just one tiny parameter in an algorithm in a real life system. So it was about, I think 8 months of work overall, building the entire system and so on. So after we built this, we said, well, so we have this type of searches. So we have exploratory and lookup, and we was like, can we then support these 2 types of searches simultaneously with the same system, right? We know what the perfect exploration rate is. Now, we can also support lookup searches because we can set the exploration rate to 0. But the question is, how do we know when someone's actually doing lookup search as opposed to doing exploration? So what we did. Again, it was done in conjunction with the HCI group. So I had the students, for example, for about half a year, was simply collecting data, how people perform different type of searches. And based on this, we found out, how many documents people click on, how long they look at these documents, how long they read them, depending on the type of search they were doing. So we just used simple behavioral characteristics that you often use in information retrieval. And we thought, based on the first search session, we'll be able to then collect this data and automatically detect whether someone is doing lookup or exploration and adapt the system based on, and adapt the C parameter based on the user behavior in the first search page. Okay, so based on the data that we collected, my student built a simple decision tree. It was published in an HCI conference, so they expect all the algorithms to be easily visualized, so that's why I decided to go for a decision tree, where basically based on query length, reading time, and cumulative clicks, we can simply decide whether someone is doing lookup or exploration. Right, so on the first page in our search system, the interface sends the query length, reading time, and cumulative clicks of the classifier, and the classifier uses the decision tree to predict what search type they are conducting. So this is the simple overview of the final system that we have so far. So you can see there's interface. Interface sends all the information that I've just described, so there's clicks, query length, and reading time to the classifier. The classifier says, I think this person is doing lookup, so we set the C value to 0. If the classifier says, I think this person is exploring, we automatically set the value of C to 1. And at the second iteration, we get different types of documents being suggested to users. In order to test this hypothesis, again, we run so our hypothesis that this type of adaptive search system that automatically adjusts the exploration rate according to task type will highly improve user performance in general. So again, we conducted a user study with 18 researchers from the computer science department, using the same system we had before, which is about 1 million arXiv documents. It was within subject design, so each subject performed 2 tasks. One was exploratory, so we basically asked them to look for documents related to their current dissertation that they were writing, and one lookup. The lookup task was a bit more difficult to design, so what we did, we asked them to come to our office a day before. We gave them a paper with the title and author covered, and we just said, go through this paper. We didn't tell them why, and then the following day we said, just look for this paper that we showed you yesterday, try to find it. So that was the lookup task. And again, in the experimental setup, we had the full system with a classifier present. So the classifier would try to detect whether what type of search we're conducting. There was a system where the exploration rate was set to 0, so it was not exploring at all. Now, what do we get out of the experiment? So the overall accuracy of this classifier was 81%. So we thought, for information retrieval tasks, there's actually quite a high accuracy if you look at information retrieval conferences and so on. We also noticed that actually users behave in the way that you would expect from what we get from the literature, information science, and so on. So we had high number of interactions and exploratory searches when the system behaved according to what the users would expect it. So it's the full system where the classifier worked and detected whether someone's doing lookup or exploratory search. And also, according to the existing literature, we also found that users spent more time per iteration or exploratory search task when the system was fully calibrated. Overall, after each experiment, we gave the users all the list of documents they clicked on, and we asked them to rate these documents, how relevant they think they were to their search. So overall, when users were using the full system, which was more exploratory, they said the documents were much more interesting and more useful. It is obviously a subjective measure, but this is what they were looking for. They were looking for documents that were interesting just for them. So in summary, what I wanted to show, I presented an approach for designing adaptive information retrieval systems that can support both types of searches. It is now a developing area of information retrieval in general, so quite a hot topic. And with these systems that can automatically detect what people want, the perceived quality of retrieved documents is higher compared to non-fully optimized system. I guess that's what you expect. But in general, what I wanted to show is that I wanted to show the importance of human input when designing machine learning-based retrieval systems. So obviously having very good algorithm, very good design is great, but calibrating this type of system is also very important. It's probably as important, even more important than the algorithm itself, and it may take a long, long time. Thank you. I'm looking for some cloud service where I can put it. But yes, you can use. Well, yes, in theory it could be used, but I just have to find a place to put it.
I was wondering what would happen if you would expose this C as a slider or something for the users. Have you considered that, or what do you think? Users learn to use this slider themselves so that they could adjust it so that they
Yeah, I think that's a very interesting question, and it's normally asked a lot by people who are not actually HCI people. So if you look at HCI literature in general, one of the basic things they tell you, and it's one of the basic findings, is that you shouldn't probably let user interact, mess up too much, because with underlying algorithms, what happens is that people just keep on trying different things, they're not patient enough to actually try it long enough to see what the result would be. They just try it once and they say, it's not what I expected. They try it again after one iteration, it's not what I expected. And actually, it's even more dissatisfying that having an automatic sort of pickup as we have with the decision tree than letting them set it themselves. Also, they don't know what to expect. I mean, if you tell them, it goes from 0 to infinity, you can set it to whatever you want, and they set it to 200. I mean, what is it they should be expecting? Like, they don't even know what to expect. But additional thing that we've been trying to do, we've been trying to actually conduct user studies now, where I think they have to be redone, where we set this C parameter to much fine-grained values of C, and then see how this will affect the search behavior and so on. So, trying to make it much more fine-grained, not just a binary classifier. Mm-hmm.
they would have to learn. Do you think there could be some other way of getting user feedback? Like, no, I think this is too random.
Yes.
Like getting some feedback.
Yes, so a good way of getting feedback is to actually not letting users control the specific parameter, but actually respond to, for example, latent variables. So they can tell us, I don't like, for example, these key phrases present in this document, or I don't like this entire group of documents. So, from this respect, it does help a lot. We have other systems where the visualization is much more complex and so on, and where we let users respond to, for example, latent variables, which are key phrases used in the documents, and this helps a lot. Well, as I don't know how much can you know. Obviously, I know that there's a lot of personalization going on in Google. I'm sure you can notice it yourself. You use your laptop and then someone else's. You type in a certain query and the results will be different. So they do use a lot of personalization. Obviously, they use personalization from multiple sources, because if you have a Google account, you'll be looking for images, they will have your emails and everything else. So yes, I know they use it, but what they do precisely, I don't know.
It would be great to track the facial expression of the user while it's doing the search, because I guess getting just the clicks is it's not very much improvement.
Yes, well, actually, we tried using eye tracker for one of the experiments. The results actually didn't improve anything. I guess part of the problem is that you have to calibrating the eye trackers all the time. Like, after a couple of iterations, you would actually have to recalibrate it, which is very disturbing to the user as well, and it disturbs the flow of the search. So we'll be thinking of using much simpler technology like Kinect, which doesn't really require that much calibration. You could probably just use it without disturbing the user too much. Yes, for example, yeah. Mm-hmm. And how dispersed your gaze is, whether you're just fixating on one area of the screen or whether you're just looking everywhere. I mean, these are very good indications, but as I said, using the up-to-date eye trackers actually require too much calibration too frequently to be reliable.